Our project this semester was to perform emotional voice conversion using a variant of GANs called StarGANs. So what is emotional voice conversion? Well, it takes an input audio like this,
I think it'll encourage me.
generates happy sounding audio,
I think it'll encourage me.
and sad sounding audio.
I think it'll encourage me.
Here's another example,
We have been fine, haven't we?
the happy generated audio
We have been fine, haven't we?
and the sad generated audio.
We have been fine, haven't we?
So emotional style transfer is really tricky because prosody is not that easy to extract from semantic contents. Another thing that we noticed during this project was that generating audio is really tricky, especially crisp and clear audio. But we were motivated to pursue it because we found very interesting use cases for this problem, namely like AI generated audiobook recordings based on text, making Alexa or Google more human and more emotional to be more appealing, automatic voice acting in video games or video tutorials, as well as even customer satisfaction during recorded phone calls, etc. So the baseline that we chose for this project was from an ICA-SSP 2020 paper called StarGAN for Emotional Speech Conversion, validated by data augmentation of end-to-end emotion recognition. So originally, the dataset used by this paper was called the IMOCAP dataset. However, we wanted to train it on a newer dataset that, according to recent literature, showed more promising results. And as an extension to this baseline, we proposed a pre-trained speech emotion recognition model that would provide continuous emotion embeddings rather than one-hot encoded emotion labels.
And this new data set that we trained on is called the emotional speech data set. It was published in 2021. It uses 20 voice actors speaking 350 sentences in 5 different emotions. The audio is of short duration, around 3 seconds each. We split the data set into a training set and a testing set using a 90% to 10% split. The data set has WAV files such as this one.
Another one, $10,000.
But before we can put that into the model, first we have to convert it into harmonic frequencies or spectral features using a vocoder that performs Fourier transforms and dimensionality reduction. We put the spectral features through our model, which performs the emotion conversion, and then we uncompress the spectral features, put it through a speech synthesizer, which generates the output audio.
Another one, $10,000.
So our model architecture goes like this. We input an audio file into a pre-processing segment, which extracts the spectral features of the audio that we want to input into the model. We then input that into a generator, which consists of an encoder and a decoder that converts the spectral features with the target emotion. The target emotion is provided as one-hot emotion labels. We then run that through a discriminator, which determines whether the generated audio is real or fake, as well as a pre-trained SER as an emotion classifier, which classifies the audio. We then pass it through a post-processing loop, which combines the spectral features with the other extracted features from the vocoder and generates the output audio with the target emotion. As an extension to the baseline model, we also propose to include a pre-trained speech emotion recognition model that would provide continuous emotion embeddings rather than one-hot encoded labels to provide better fine-tuning of results.
So these are what the training curves look like. One training curve for the discriminator and one training curve for the generator, which are trained in tandem together. Now, training was rather difficult. The audio after the first 50,000 steps of training sounds like this. The audio after the 150,000th step sounds like this. And only after 300,000 steps do we start to hear comprehensible audio.
I hope we get help.
Now, as you can see, these curves don't seem to converge very much, and that sort of reflects in our results. In order to evaluate our models, we use a distance metric called Mel-Septual distortion, which compares our generated audio to the original reference audio. As you can see here, our distance metric has outputted slightly more distant audio than the reported results. And we suspect that's because we simply don't have enough computing resources to train the GAN enough to generate very crisp sounding audio. But what have we accomplished here? We trained a full StarGAN from scratch to generate comprehensible audio and in different styles. One really cool innovation of the StarGAN is that it's able to generate many styles of audio from one source audio. With that, we thank you for listening. And as a bonus, you get to hear some more generated audio.
I hope you enjoyed yourselves.
Or we hope you learned something.
I hope you enjoyed yourselves.
Thank you.